visible, right?
Yes, sir.
Okay. Just a second. Okay. Visible now?
Yes, sir. Visible, sir.
Okay. So I will be talking about the support vector machine and some of its application. When we talk about the support vector machine, there was a time that it used to have the same position as we have the deep learning now, all right, in terms of the machine learning models. So when we talk about the machine learning, basically it's a way of learning. Then based on those learning, we predict something and then we identify whether that is correct or not, and then we improve again. So I will ask some questions and then we will move to the SVM. Can you recognize these pictures? Hello. Okay, what are these? Okay, Ganeshji and India Gate. Okay, yes. Now, now the question is whether this first one is a portrait or a sculpture. All of us can identify sculpture. Okay, from which place? No, no, it's not AI generated. We do have real images, which is very high definition. The second image, all of us, yes, it belongs to the Mumbai, one of you correctly mentioned. So this second image, all of us can identify is the India Gate. So it's not necessary that we have visited this India Gate and we were standing from this particular angle, and then only we are able to identify, okay, that from here, uh, this is a India Gate, right? If we must have across these in either TV, some images, or over mobile, or personally I visited over there. Right now, the question is how we recognize it. Right. This first image is basically from Lal Bagh Bagshaw from Mumbai. So we learn from our environment. So as you can see over here, this brown cat, it ring the bell over here, and then this white cat observe this phenomena, and correspondingly it also ring the bell. So the master fed it, right? So basically learning is similar to these. Either you are self-motivated, or if you can be motivated from by looking at the others phenomena, other examples. So learning is way of constructing or modifying representation of what is being experienced. And based on these feedback, we can divide the machine learning into three parts. One is the supervised, unsupervised, and reinforcement learning. Uh, Over here, you must have come across different machine learning methods for the supervised learning. In case of the supervised learning, what or all these learning, what we are interested in modeling, right? So modeling is nothing but we want to come up with a function like this, right? So for every x, I want to know what is y, right? So in supervised learning, that y is already there, right? Because it's a label data, right? The data that we have is labeled in over here. So in this, let's say I am having 1, 2, and 3, and correspondingly my output is 1, 4, and 9. Then easily I can identify that, okay, my f of x over here is x of a square, right? Now, if I say that my 5 value is there and the value is 20, Now what I need to do? I need to subtract some delta from here, right? So as soon as we have more number of the samples with us, we update our model. This is in case of a supervised learning, right? So in supervised learning, it can be divided into two parts. One is the classification, and another is the regression. In case of the classification, what we do, let's say, based on some particular parameter x1, x2, and x3, we need to identify that what is the price of a flat, right, of a room or a house. So if we identify that, okay, it is, let's say, 65 lakh, right? And based on that, if I can also identify whether I will buy it or not, yes and no. So this problem is the regression problem. This one is the regression problem where I am coming up with a continuous linear value. And based on that, if I want to come up with some classes, yes, no, healthy, unhealthy, so that is part of classification. In case of unsupervised learning, we have only X with us. Right here, for every X, I know the Y also mapping is there. So based on the inherent property of the X, I try to identify that how can I come up with some groups. Right, so we called it as a clustering over here. And the third type of the learning is the reinforcement learning, where I have nothing with us. Right, I take some action randomly, x1, correspondingly I am having some reward 1, and I change my state from S to S1. Yeah, S from S1 to S2. This is what reinforcement learning is. So in the case of the reinforcement supervised learning, as you must have come across, that we need to come up with a function. Now we are not having the input like this. All of us are engineers, so instead of 1, 2, 3, now my input is in the form of some images, in the form of some waves, right? For time series data or text based data. And then we try to map again. So in case of supervised, the data is there. We need to label it first, and then we train, and then we test, right? So in tomorrow's session, I will talk about that whenever you are getting a result, then how to identify whether it is valid or not. So we will be talking about some parametric test in it, t-test. Now, for these, we have different models. So, logistic regression, perceptron is there, Navis Bayes is there, neural network, decision tree, K nearest neighbor, and SVM. So, today we will talk about the SVM. It was proposed somewhere in 1996, even though they started their work in 1990, and then they come up with the support vectors for function approximation, regression estimation, and processing. This is their paper. If you are more interested, you can also always refer this paper. Now, this SVM is widely used in machine learning because it can handle both linear as well as the non-linear classification tasks. And the idea over here is that to come up with a boundary so that we can easily segregate the different classes, right? So when the data is not linearly separable, we come up with some kernel function. So what happened over here? Let's say this problem is there. This particular data set is given to you. Now tell me which algorithm you will use on it and why. Yes, anyone, please answer. Hello. Am I audible or not? Think you are studying different machine learning technique, and just any idea that which algorithm we can apply over here, or what should be our approach. Okay. Okay, clustering approaches we can apply, KNN we can apply. Or what we can do, can we convert this particular representation over here? I'm having two variables, x1 and x2, in such a way so that I can classify it with a simple linear line. Line equation we know y equal to mx plus c. So can I convert this into some particular dimension, some particular representation so that in that dimension with a single line we can divide? This is what SVM try to do. So what we can do, we can consider the z as x1 square and over here x2 is there, so x2 square, right? And then if we apply this over here, all the data point will be like this, right? So now we can divide this with a single line without actually using the complicated maths. So from one dimension, we try to convert it into another dimension phi x so that we can come up with a linear classifier over there. This is the main idea of SVM. That's why it is also known as a, kernel machine, right? Because we called it as a kernel function. So this is a discriminant based method with defined by separating some hyperplane. So this particular plane over here, as you can see this line, this one, right, is a kind of plane. We try to learn class boundaries over here, and support vector consists of the example closest to the boundary. So we will discuss what is the meaning of it. So what we want to map the instance space to a higher dimensional space where some linear based method is sufficient to divide it, right? So defining that kernel function is a crucial factor in SVM. We will discuss how to decide that. SVM has a clever way to prevent overfitting. This may be, it can use many features without requiring too much the computation in it, right? And it was among the best performing classifiers before the deep learning, as I was telling. So SVM has a lot of application. You can use it in the image classification, segmentation, sentiment analysis, bioinformatics, financial fraud, spam, basically classification related tasks. Beside classification, it can be used in the text generation, text categorization also, machine vision, anomaly detection, some regression based problem. For that, we have SVR specifically, support vector regression, time series based analysis. It can be used in not only in computer vision, but it can be used in almost all the fields, whether it is electrical, electronics, mechanical also. So if you remember, in case of the logistic regression, what uh, we have this 1 upon 1 plus e raised to power minus x. So we can say that at 0.5, right, we do have different confidence. So over here at 0.5, the confidence is same. Now what we can do, just a second. So we can predict over here that it belongs to 1, here it belongs to 0, right? If my that I can write it in the form of the conditional probability is that what is the probability of y equal to 1 given that x is there. So we with a hypothesis as not, right, in that we are having a theta tx, right? This is in case of logistic regression, if you remember. So we can say the larger the value of h naught. So if we go over here or over here, right, the larger is the probability and higher is the confidence over here. So there is low confidence when the value lies at here. So similarly, the confidence prediction of y equal to 0 if it is very less than the 0. More confidence of the prediction from the point located far from the decision surface. So what is the meaning of it? Let's say over here we are having a boundary, right? This in this case we these are the different fields. So we what we can say that these farmers, right? So this particular position and this particular position, it is very clear that it belongs to the farmer 2 and this belongs to the farmer 1. Or this belongs to a country 1, this belongs to the country 2. As you can see over here, we do have fences, but the major dispute is over here, the boundary cases, right? There is no dispute in these cases. So we try to come up with a line so that it is equidistant from both the points, right? So that whenever a new test case is there, it can easily identify, okay, it belongs to the class 1 or class 2. So what we used to do earlier with the help of the Bayesian, we consider these different points right over here. So let's say this is the point for another class. So we give the weightage to all these points, and then we try to identify weight each line by its posterior probability, right? But in these cases, I have to consider lot of such particular points when I know that this point belongs to the class 2 or this point belongs to the class 1, like that. So what is the another method? We take the help of the support vector, the line that maximize the minimum margin. So support vector are those vector, right, which using those particular support vector, for example, over here, right, this is class 1, this is class 2. So for class 2, I am having 1, 2, 3, 4, 5, 6, right? 6 points. And likewise, for class 1, I'm having 1, 2, 3, 4, 5 points. 5 points over here, 6 points over here. So in the traditional methods, right, in other methods, what we try to do, we try to identify all these points and then we take some weightage. While in case of the support vector machine, because there is no role of this particular, if a new point is over here, there is no role of that point in identifying whether it is class 1 or class 2. Why? Because it is already with more confidence, we say that it belongs to the class 2. The main issue is with those particular points which are at the boundary. So this particular point, let's say I'm considering this as a line equation or this is a boundary. So the nearest point, right, data point to the boundary is called as the support vector. So these support vector help us in identifying whether it is belonging to one class or another. So what we try to do in those cases, for example, over here, the circle one are the support vector. Then we try to come up with a line that maximize the minimum margin. Now, minimum margin is over here. Let's say the distance. This maximum margin separator is divided by a subset of the data point, as we called it as a support vector. That's why its name is support vector machine. So there are different type of the margin. Mathematically, we can represent one of the margin as a functional margin. It is considering a point of xi yi with respect to w and b, because my line equation is y equal to mx plus b, right? So we measure the distance of the point xi yi from the decision boundary, right? For example, this w we consider, b we consider as a line equation, and then we say that larger this functional margin is, more confidence for correct prediction is. But the issue over here is that, let's say my line equation is this, 2x plus 3y plus 1 equal to 0. I can have another same line with different scale, right? For example, I can multiply it with 10, then this one. So this W and B can be scaled to make this value larger. So what we can say, out of these, the value, the margin that is having the minimum value, we will consider that as a functional margin. So instead of this functional margin, we go with the geometrical margin. So, and this geometrical margin is invariant to scaling, right? For a decision surface, W over here and B, so this is a vector, right? And let's say I'm having 2 point P and Q. So P point is having A1 and A2, and my Q point is B1 and B2. So the vector orthogonal to this is given by W as we consider, and the unit length orthogonal vector is WY, absolute value of W. So for this case, if my line equation is 2x plus 3y plus 1 is 0, right? So my W value are 2 and 3 over here, and thus it came out to be 2 under root 3 and 3 under root 13, 2 under root 13. 13 a square plus b square under root. Then we can say I can represent my P as P equal to Q plus this margin into the length of a vector. So this I can consider as, so I can write my Q as P minus gamma W vector, right? So I can write this as my Q point as B1 and B2, and P point as A1 and A2 with respect to this. Considering my line equation is this, W transpose T X plus B. Because mathematically we can represent the weights in this way. This is the representation of a line when we code, let's say in Python or another language. So what we can say that that margin, right? So we replace the values over here in this. So my margin is W transpose A1 A2 plus B divided by this W. And then we can rewrite it in this way. So this is actually my margin. And over here, I can consider this vector as a 1. So my margin came out to be this. And what we are interested in, if I am having multiple such points with me, then I will come up with the smallest of the geometrical margin of individual point that satisfy the given condition. That it should be the minimum for all the possible margin, right? So another point is over here. So the distance from here to here, then we try to identify that which particular point is having the minimum margin, and that particular point we will consider as a support vector. And let's say this is the margin that is the smallest one among this. So we can come up with a different line, as you can see over here, different line equations are there, and we need to come up with that margin with maximum margin, right? From all the possible. So as you can see over here as well, we try to come up with optimal margin case, right? Optimal hyperplane that divide the data points very well. And the distance between the optimal hyperplane and other hyperplane is called the margin. So this is my optimal hyperplane, and these are other planes. And the closest data point are known as the support vector. So over here, this is support vector, this is support vector, this is also support vector. When we are choosing the optimal hyperplane, we will choose that hyperplane which is at the highest distance from the closest data point. It is important to remember. And if we choose the optimal hyperplane very close to the data point, as you can see here, right? then margin will be very small and it will generalize well for training data, but when unseen data we give, it will fail to generalize. So our goal is to maximize the margin so that our classifier is able to generalize well for unseen case also, not only for the training sample, but for the test samples. This is our aim. Right, as you can see over here, we want to come up with this hyperplane so that it can divide, right? If this is my particular representation, I convert it into some hyperplane so that in that hyperplane with a single line, I can divide. So we assume the linear separability trading example, as I told you, the classifier with the maximum margin width is robust to outliers and thus has a strong generalization ability. So what we try to do over here, we are, let's say, having two lines, right? Uh, in that we consider, for example, in this case only, we consider that we keep on changing. We want to come up with this optimal hyperplane, and this line we keep on changing, right? And till this for that particular margin, the data points are sufficient enough so that we can divide these two classes well. So, so we can say over here that we want to scale this margin as 1, right? Subjected to the maximization of this particular equation. And maximization of this particular equation is same as minimizing W square. That fulfills some of the constraints for all xi and yi, right? Now, what we are interested in, that we need to come up with a plane, right? So that we can apply the optimization algorithm to come up with a solution for this particular problem. So let us consider one particular example. So as I was telling that we can consider a line in that I am having some data points. Right over here, this is my hyperplane 2, this is my hyperplane 1, and this is my optimal hyperplane, right? And in that I am having that W with me. And over here I can say that HXI is +1 or -1 if that my line, depending on the line equation, W dot X plus B is greater than equal to 0, then we say that it is +1. If W dot X plus B is less than 0, then we say that it is -1. It is classified as +1 and -1, these two classes. When we combine these two equations, we can write it as yi W dot xi plus b -1 should be greater than equal to 0 for yi plus -1. So now we can say that let's say I am considering my data point as B. That's 4 minus 4 with 3. So correspondingly, I'm having a plane as 2x minus 2y plus 5z. So we can say that this is the distance of h1 and from the origin. So we calculate the distance, and my distance in that case for this particular line will be 2 into 4 plus minus 2 minus 4 plus 5 dot 3 plus 8 under root of 2 square plus minus 2 square plus 5 square. So we know that it starts from the mark 0 0. So my h1 will be a x1 minus x2 plus b plus 1 equal to 0, right? Where my w x plus b is minus 1. So likewise, distance from the origin and h1. For this case, using the same formula over here, we say that it is 0 dot a plus 0 into minus 1 plus b plus 1 divided by under root of a square plus minus 1 square. It came out to be as b plus 1 divided with the unit vector. Similarly, we can calculate with another hyperplane h2, right? Where my h2 is ax1 minus x2 plus b minus 1 equal to 0. So the distance between the origin and the h2 0 comma 0 and h2, it came out to be as, if I put the same value in this, it came out to be b minus 1 vector. Now if I want to calculate the margin now, the margin maybe, because that we are interested in. So margin will be h1 minus h2. So if we put the values over here, the h1 b plus 1 weights minus b minus 1 weights. Right, so it came out to be 2 by, if we can come up with, our aim is to maximize this margin such that it follow the line equation, these. So in linear regression, we try to create a gradient descent and try to minimize the distance throughout the derivative. But we cannot use the gradient descent directly over here, because the SVM optimization problem is a case of constraint optimization problem. And it is always preferred to use the dual optimization algorithm in these cases. Right, so we try to come up with the constraint optimization problem using the duality or dual optimization algorithm. Right, so this is what I was talking about, that the margin over here is now 2 by W. Right, considering that this is my optimal hyperplane with two plane h1 and this is the h2. So for that we can use this Lagrange method also. Only a few margin point can be non-zero, call the training data point whose margin are non-zero, the support vectors, right? And our aim is to convert or to solve this problem, right, using the Lagrange function. I'm not going into detail of the Lagrange right now, but using that method, you can optimize these. Now, what if the data point is not linearly separable? Because this is the assumption that we consider that the linear point should be linearly separable. The data point should be linearly separable, or some noisy data points are there. So for such cases, we use a concept, we call it as a kernel trick. For example, this particular problem, right? We can try to convert it into such a representation so that with a single line we can divide it, and this is known as the kernel trick. So this transformation of z as x square plus y square is called as a kernel. So what we want that using that kernel, we can come up with a minimum value. Right, so the objective to minimize is to minimize this w square plus some c. That is the error. We add some penalty variable, this one. Correctly classified example far from the margin, we call it as 0. Correctly classified sample for the margin is 0. Then the value of the margin may be between 0 to 1. We do have another type of the short margin hyperplane as well, where data is not linearly separable. We try to come up with a hyperplane with the least error in those cases. Right, so we come up with a hyperplane uh, where we are having the minimum error with us. And when we talk about these hyperplane, right, these hyperplanes uh, is a plane that linearly divide the n-dimensional data into two components. If it's a two-dimension hyperplane, we call it as a line. If it is more than two-dimension, or let's say three-dimension, is a plane, and likewise. So we take the help of the kernel, as I told you that from one particular representation, we convert it to another using the kernel trick, right? So now easily, if I apply the x1 square plus y1 square over here, now with a single, this particular plane, we can divide it into two parts. Now, in the kernels, right, as you can see over here, this particular dimension. So kernel are nothing but they are representation of the data point in some new dimension of the same data point. As a human, we are able to visualize only three dimension, but these kernel functions try to help us to visualize that in another dimension where a linear or linear classifier can be used to just divide. So now the question is how to decide the kernel, right kernel, right? Because that play an important role. So kernel is basically the original input attribute is mapped to a new set of the input features via some feature mapping. Since the algorithm can be written in terms of the scalar product, we can replace xa and xb with phi of xa and phi of xb. Here phi is a simple operation in two dimension in a low dimensional space that can be used to compute the scalar product of these two data points or images in high dimension. So there are different type of the nonlinear kernels, right? So what we can do, we take the help of the dot product of the feature vector in both the training and test, and then we come with a kernel function. A kernel function is defined as a function that corresponds to a dot product of two feature vectors in some expanded feature space. So these are some of the mostly used kernel function in SVM. Linear kernel is there, polynomial kernel is there with some power of q. Then we do have Gaussian kernel, it is very popular. Also, we have this RBF in it, radial basic function with this formula. Then we do have the sigmoid kernel as well. So in general, we can come up with any function as in SVM if it fulfill the markers conditions. So as you can see over here, this is a linear kernel. This is a two-order polynomial. This is eighth order. This is fourth order. We need to see that what order it may fit, or we can go with the RBF also. This is a uh, snapshot of how the Gaussian kernel work, right? So Gaussian may lie in this way also. When we talk about the performance of the SVM, they work well in practice because we are more interested in only those particular vectors which are on the boundary, right? The user must choose the kernel function and its parameter very precisely, because then only you will be able to come up with better algorithms. They can be expensive in the time and space for a big data set. So the kernel trick can also be used to do PCA. So we can apply the PCA also if I am having a very high dimensional space. And this is what we used to do in case of, let's say, face recognition problem. First we apply the PCA, then we apply the support vector machine on that. So for the tune, some parameters are there. We can tune them using the kernel function, regularization method, some gamma and margin. So these are the main parameters that we deal with in case of SVM. So this kernel, as we can see, we discussed are of different type. Another way is this regularization parameter. In the Python, it is commonly represented as a C. It indicates the SVM optimization, how much we want to avoid the misclassification in the training example. Now let's say over here, this is a low regularization value. This is a high regularization value. Now what is the meaning of it? A very small value of the C will cause the optimizer to look for a large margin separating hyperplane. Misclassification due to the lower regularization value. For a large value of the C, in this case, the optimization will choose a smaller margin hyperplane. Now, this margin is a separation of the line to the closest class, as you can see over here. A good margin, this is for a good margin, where the separation is large for both the cases, right? While in case of the bad margin, this line will shift to one of the data points, one of the classes. So as you can see over here, this is a bad margin. Then we do have a concept of the gamma. It defines how far the influence of a single training example reach. So if I am having a low value, then I am able to reach to more space. Points far away from the separation line is still it's in influence. If I am having a high value, points close to this line are considered in the calculation only. Now we can use it for the multi classes, right? In that, basically it work with, let's say I'm having three classes. As you can see, yeah, as you can see in this also, C1, C2, and C3. So even though SVM, we consider that we need to come up with a line so that it can divide only class 1 and class 2. But if I am having multi-classes, in those cases, what I can say, I can consider C1 with all, right? We come up with a kernel that learn the separation between class 1 and rest, similar to class 2 and rest, class 3 and rest, and likewise. In this way, it can be used for handling the multi-class classification. We have also worked on this multi-class classification at SVNIT. We do have one research group by the name of Computational Intelligent and Smart Motion Research Group. In that, we worked on the motion analytics part basically. And along with that, we are also trying to use the different computational methods on the brain-computer interface, on the robot planning, on the uh, robotic hand as well, and other applications. So this is one of the application that we have tried using the SVM, in that we tried to see that based on the walking, can we predict some angles, right? So when we walk, actually, we see only the person, but with the help of the computation method, we are trying to come up with these angles. We call these as a kinematic parameters, right? We also, if we identify the pressure over here, we called it as a kinetic pattern. So in this particular study, what we did based on the previous input, we tried to identify using SVM the next particular gate cycle. We come up with one patent also on this. So as I was telling you that based on the human walking, we have a lot of applications. So human gait, we call it as a gait. So gait consider is a locomotion from one particular point to another. There are different ways: walking, running, jumping. All these are part are of the gait. And an average adult take 5,000 to 8,000 steps a day. Research associated with the mechanics of the human body during locomotion is basically known as the gait analysis. It can be used in the gait rehabilitation. We try to apply this SVM based approach on this gait rehabilitation. Then we apply it on the uh, gait recognition also. We apply it on the sports. We can apply it in the sports as well, right? So we see that how we can apply the SVM or SVR specifically over here in case of the robot, so that we can come up with some assistive as skeleton. So for the same, we have prepared a data set at the Raman lab only. In that, we apply the four cameras, and then a person or a subject walk in front of it, and then based on that, we come up with this trajectory. Now, my aim is that a certain time what happened, that a particular person meet an accident, and because of that, he or she is not able to walk properly. So, can we come up with a assistive tool so that it can help the person to walk again, right? So this is the pattern that we exhibit. So based on our data set, we predict all these type of the patterns, as well as the angles also, kinematic parameters also. Kinematic parameter, in that we come up with the different angles: hip angle, knee angle, ankle angle, and like that. And now, if I can know that, okay, this is the body build of a person, so based on the anthropometric features, that is the body build, we can identify that, okay, how this particular person will walk in a given scenario. So based on that, what we did, we let's say I'm considering the knee angle, then we apply the different methods such as the Gaussian process regression is there. We come up with the random forest. We also apply the SVR on it with the RBF kernel. Then after that, we apply the filters so that we can come up with a smooth output. So as you can see over here, we apply these different models: Gaussian progression, support vector regression, random forest, and the R value in that, even though it was the GPR was giving the best possible R2 value, and still this SVR, the support vector, is providing good reference in it. We need more data so that it came out to be more precise. So with this, I end my session. I'm thankful to the advisors and the researchers from whom I am able to get this result. Yes, I'm open for the questions now.
Hello, participants. Please, if you have some doubt, some query regarding this SVM, please you can ask here on the chat box. This SVM as per my knowledge, this SVM is the toughest algorithm in the machine learning. The mathematics is very tough. It's very difficult to understand. So, sir has nicely explained the each and everything regarding this SVM mathematical intuition. So now, any one of you are having any doubt regarding this SVM? Now, please ask question.
Yes.
So I cannot see any question, any doubt in the chat box. So I am hoping that everything is clear to you. So okay, sir. So thank you very much for taking this early morning session. Yes,
Thank you, sir.
one
Yeah.
doubt how we can use SVM for speech classification.
In speech classification, basically, what do you want to do exactly? Because there are two ways. One traditional method, if I talk about, then you have to identify some of the features from that continuous time series. Once you identify those particular feature, then you can apply the SVM based on I hope this Gaussian regression, Gaussian kernel may help you in that case, classifying the speech by age group. Okay. So you must be having some label data with us. So the first step is that you need to you need to extract those features, right? Another method is that nowadays we have LSTM and RNN and transformers. So you can you can give the raw data to the LSTM and other, and then later on at the end we can apply instead of the softmax we can apply this SVM as a classifier, and then you can cross check. This is only just a suggestion until unless you will not we will not discuss more about the problem statement. We cannot say that this will work correctly or not. Certain time we need to fine tune also. Okay. If still you have any doubt, you can drop me a mail on cprakash@cod.sv90.ac.in, or you can Google me. We will connect. We will connect tomorrow also. If you still have any doubt on SVM, we can discuss at that time.
Yes, so tomorrow the same time, sir, that will be having one more lecture. So if you still having some doubt in SVM, or just you can see the schedule, this timetable. So if prior, if you read something about this next topic, then you may ask very good question on the this tomorrow this session. So now we will wind up this session, this first 1 hour. So next, after 15 minutes, Professor Rajesh sir will come and he will take this gradient boosting and this gradient boosting and XG the topic, the session. So
Thank you, sir. Thank you
thank
for
you,
the
sir.
invitation.
Thank you, Chandraprakash sir. Thank you very much. Thank you.